Okay, let's unpack this. Think about our home galaxy, the Milky Way.
Yeah.
It's just this enormous, spiraling island of stars, gas, dust, billions of them.
hmm
But how big is it, really? How fast does it spin? Where's the actual center? Answering those really basic questions about our cosmic home,
Yeah.
well, it all hinges on knowing one key number.
Yeah. The distance from us here on Earth right to the heart of the galaxy, what astronomers call the galactic center distance, R0 or R naught.
R zero. Yeah.
And that distance, R0, it's not just like a fun fact, it's probably the single most fundamental scale link for understanding the whole galaxy.
Okay.
It basically sets the scale for almost everything else we calculate about the Milky Way, its total mass, how fast it's rotating, the orbits of stars, how we piece together its history and evolution. Getting R0 right is just crucial.
Absolutely essential for drawing the map, basically.
Exactly.
And figuring out that number, well, it's been this huge scientific effort for, over a century now, packed with challenges, clever ideas, and ever-improving measurements.
Definitely. And we've got a good pile of source material for this deep dive, some classic papers, yeah, but also a really interesting review looking at the latest results, especially, from the Gaia mission, which is changing everything.
Okay, so our mission here is to kind of trace that whole scientific journey. We'll look at why measuring R0 has been so darn difficult, explore the different techniques astronomers have cooked up over the years, look at the newest, most precise results, and really try to understand what Gaia brings to the table, why it's such a game changer.
Sounds good. Let's get into it.
All right, so first things first, why has measuring this distance, R0, been such a tough nut to crack?
Well, number one, it's just really, really far away. I mean, we're talking somewhere in the ballpark of 7.5 to 8.5 kiloparsecs.
Which is, translate that for us.
Oh, right. Sorry. Roughly 24,000 to 27,000 light years. It's a long way off.
Yeah, that's vast.
Exactly. And at that kind of distance, let's say, the classic way to measure distances in space trigonometric parallax, it just wasn't really possible with the older telescopes.
That's the thing where you see how much a star seems to shift against the background as Earth goes around the sun, right?
Precisely. The closer the star, the bigger the apparent shift. But for something as far as the galactic center, that shift is absolutely tiny, way too small to measure accurately from Earth, or even with earlier space missions like Hipparcos, actually.
Okay, so sheer distance is problem number one. What else gets in the way?
A massive obstacle literally is interstellar dust.
Ah, the smog of the galaxy.
Pretty much. The galactic center is hidden behind this really thick curtain of dust right in the plane of our galaxy. And this dust, it just gobbles up and scatters visible light almost completely.
So you can't just, point a normal telescope that way and see it.
Nope. Forget optical telescopes. You have to rely on observing in infrared or radio wavelengths. Light at those longer wavelengths can punch through the dust much better.
But even infrared, the dust still messes things up a bit, right? Like if you're using standard candles.
Exactly right. Standard candles, those objects like Cepheid variables or RR Lyrae stars where we think we know their true brightness, the dust still dims them as the light travels towards us. And the real problem is the amount of dimming, what we call extinction, it changes depending on exactly which path the light took through all those patchy dust clouds.
Ah, so it's variable. Makes it super hard to judge the true distance just based on how bright something looks.
Super hard, yeah. And then there's another, maybe more subtle challenge, just deciding what you're actually measuring the distance to.
What do you mean? Isn't just the center?
Well, yeah, but what is the center, technically? Are you aiming for the supermassive black hole, Sagittarius A?
Okay.
Or are you trying to find the spot with the highest density of stars? Or maybe you're after the galaxy's dynamical barycenter, its actual center of mass, the point everything is orbiting around?
I see. And those might not be in exactly the same spot.
They might not be. Probably very close, but maybe not identical. And different measurement techniques might naturally be pointing towards slightly different definitions of center, which just adds another layer of uncertainty.
Right. Okay, that makes sense. So if direct parallax was out and the view was blocked by dust, how did scientists even start trying to figure this out, way back?
Well, they had to get clever, and they had to make some big assumptions. Early methods, like the ones Harlow Shapley used way back in 1918.
Wow, over a century ago.
Yeah, he assumed that certain types of objects were spread out symmetrically around the galactic center. He famously used globular clusters, those big, dense balls of really old stars. But also other things like certain variable stars, RR Lyrae, mirror variables, things with fairly predictable brightnesses.
So the thinking was if you map out where all these things are in 3D space, the middle of that distribution should be the galactic center.
That was the logic, yeah. Estimate the distances to as many of them as you can, plot them out, find the geometric center of that cloud of objects, and boom, that's your estimate for R0.
Clever if the symmetry assumption holds.
If it holds, exactly.
Yeah.
Other early techniques used radio astronomy. They'd measure distances to specific things emitting radio waves near the center, like H2O masers you find in regions where stars are forming.
Okay, so what kind of numbers did these early stabs give? Were they close?
Close is relative. There was a pretty significant range, which really reflected how difficult it was and how much the assumptions mattered. If you look at the results coming out from, say, the 1970s through the 1990s,
Yeah.
you see quite a spread. Kerr and Lyndon Bell in '86, they averaged like 25 different measurements and got 8.54 plus or minus 1.1 kiloparsecs. They actually suggested the IAU adopt 8.5 kiloparsec.
Okay, 8.5.
Then Reed in '93, combining various estimates, landed on 8.0 plus or minus 3.5 kilopc, a bit lower.
Right.
But then Alling and Merrifield in '98, they used completely different methods involving models of how the whole galaxy rotates, using things called Oort constants that describe local star motions. They got a noticeably lower value, 7.1 plus or minus 0.4 kpc.
Whoa, okay, 7.1 versus 8.5. That's a really big difference, especially considering the uncertainties they were quoting back then.
It is a difference of over a kiloparsec, yeah. And the uncertainties themselves were pretty large, like 10, 15% or more. It just hammered home how uncertain the whole picture still was.
Yeah, really shows how much the answer depended on how you asked the question and what you assumed about the galaxy.
Absolutely.
Okay, so time marches on. Then we get the Hipparcos mission, the first big space-based astrometry mission. Did that finally settle the R0 debate?
Well, Hipparcos was absolutely revolutionary for measuring parallaxes for millions of stars, improving distances all over the place. But for R0 itself, the galactic center was still just too far away for Hipparcos to get a direct parallax measurement.
Okay, still too far. So indirect methods again.
Still indirect, yeah. What Hipparcos did allow was much better calibration of those secondary distance indicators we talked about, the Cepheids, the RO Lyrae. Because Hipparcos could measure their distances more accurately, we could then use them more confidently to probe further out. Or, researchers used Hipparcos data to study the motions of groups of stars whose orbits should be affected by the galactic center's gravity.
Right, refining the tools. So what kind of R0 values came out of that Hipparcos era? Did the range narrow down?
It did narrow somewhat, and the uncertainties got a bit smaller, but there was still quite a bit of variation. You saw results like Feast and Whitelock in '98 using Cepheid movements, getting 8.5 plus or minus 0.5 kpc.
Okay, back up near that Kerr value.
Yeah. But Reed, also in '98, used RL Lyrae stars and got something a bit higher, 9.3 plus or minus 0.7 kpc.
Higher still.
And then Stanek and Garnovich, using a different type of star-red clump giants, observed through a clearer patch towards the center called Bade's window. They got 8.2 plus or minus 0.2 kbc.
8.2. Okay, so the uncertainties are shrinking compared to the 70s and 80s, definitely. But you still have numbers ranging from low 8s up to low 9s, depending on which stars you use.
That's exactly it. A review by Perryman in 2009, kind of summarizing the state of play after Hipparcos, basically concluded that R0 estimates were still in this, quote, rather broad range 7.5, 8.5 kpc. People often used 8.2 kVc as a kind of reference value, but it wasn't like a firmly established high-precision number.
Right. It sounds like astronomers were still really hunting for a way to measure it more directly, something less dependent on all these calibration steps and assumptions about star populations.
You got it. And that's really where dynamical studies started to take center stage, really taking off around the year 2000 onwards. And this was made possible by incredible technological leaks, especially adaptive optics on the big infrared telescopes.
Adaptive optics.
Yeah.
That's the tech that uses like wiggly mirrors to undo the blurriness from Earth's atmosphere.
Exactly, because you have to observe the galactic center in infrared light to see through the dust. Being able to correct for atmospheric blurring in real time with adaptive optics was absolutely key. It let astronomers see individual stars right near the central black hole with amazing sharpness, something unthinkable before.
Oh. So instead of relying on these big populations of stars spread out over large areas, they could actually zoom right in on the stars whipping around the black hole itself.
Precisely. That was the breakthrough. By meticulously tracking the exact movements of individual stars orbiting Sagittarius A, both their motion across the sky, called proper motion, and their speed towards or away from us, the radial velocity, you can essentially use Kepler's laws of orbital motion in reverse.
Okay, how does that work?
Well, we have a pretty good handle on the mass of the black hole, SGRA. If you can measure the precise size and shape and speed of a star's orbit around that mass very, very accurately, well, the laws of gravity directly link the orbital parameters to the distance to that central mass.
I see. The orbit itself tells you the scale.
Yes, Genzel and his collaborators were real pioneers here. Back in 2000, they used these kinds of stellar motions near SGRA to estimate R0 somewhere between 7.8 and 8.2 kpc, although the uncertainty was still quite large back then.
And this is where that really famous star, S2, comes into the picture, right?
Yeah.
The one that orbits super fast and close.
S2 is the star that made this technique famous, yeah. It's often called orbital parallax, or sometimes dynamical parallax. S2 has a relatively short orbital period, only about 16 years, and it swings incredibly close to SGRA at its nearest approach.
So it gives you a lot of data quickly, relatively speaking.
Exactly. By tracking its complete orbit multiple times now with incredibly high precision, you get a really powerful, almost direct geometric measurement of the distance to SGRA.
That feels like a huge leap forward compared to averaging globular cluster positions.
Oh, absolutely, a different league. The gravity collaboration, using the Very Large Telescope Interferometer in Chile, has been a major player here. An early result from them, around 2003, I think, using S2's orbit gave R0 as 7.9 plus or minus 0.4 kpc. And of course, the group led by Andrea Ghez at UCLA using the Keck telescopes in Hawaii, they've also been famously tracking S2 and other stars for decades. Their 2008 results from the S2 orbit gave similar R0 values, around 8.0 plus or minus 0.6 kpc, or maybe a bit higher, 8.4 plus or minus 0.4, depending on whether they assume the black hole itself was perfectly stationary.
Okay, these numbers are definitely clustering more tightly now, maybe around 8 kbc, and the error bars are shrinking dramatically compared to the earlier era.
And they've kept shrinking. The most recent, and you could argue the most precise, estimates for R0 come from exactly this S2 orbit modeling, pushing the technology to its limits.
Yeah, give us the latest numbers.
So the gravity collaboration, in papers from 2018 and 2021, they derived an R0 of 8.275 plus or minus 0.009 kiloparsecs.
Now, 0.009, that's incredibly precise.
It is. Now, there's also a systematic uncertainty on top of that, about 0.033 kpc, related to things like the reference frame. But still, the statistical precision is amazing, just a few tens of parsecs uncertainty at a distance of over 8,000 parsecs.
Okay, so after a century of effort, we finally have it nailed down. 8.275 kpc.
Well, here's where it gets really fascinating, and the source material makes a big point of this. While gravity has that astonishingly precise number, the Keck team, the group led by Tuan Do, published their own, also very precise, S2 result in 2019.
What did they get?
They got R0 equals 7.971 plus or minus 0.059 kpc, plus a smaller systematic uncertainty.
Hang on a second. Let me get this straight. Both teams are using state-of-the-art instruments, tracking the exact same star S2, orbiting the exact same black hole SGRA, and one gets 8.275 kpc with tiny error bars, and the other gets 7.971 kpc, also with pretty small error bars.
But those two numbers themselves are different by, what, about 300 parsecs?
That's it, exactly. Roughly 300 parsecs or 0.3 kbc.
Which is way, way bigger than the measurement uncertainties each team is quoting.
Precisely, and that is the current puzzle. Despite the unbelievable precision achieved, there's a significant disagreement of tension between the best R0 values from these two world-leading teams using the same fundamental technique. Why? How can that happen if they're measuring the same thing?
Well, this might loop back to that slightly subtle point we touched on earlier. What exactly is the center? These dynamical methods based on S2's orbit are fundamentally measuring the distance to the black hole, SGRA. They work by assuming SGRA sits precisely at the galaxy's overall center of mass, the dynamical barycenter.
Right. And why might that assumption not be perfectly true.
Think about it. The dynamical barycenter is the gravitational center of everything in the Milky Way. All the stars in the disk, the bulge, the central bar structure, all the gas, and the enormous dark matter halo surrounding it all. SGRA is just one object, even if it's supermassive.
Okay.
If the distribution of all that other mass, maybe the dark matter isn't perfectly centered, or perhaps the big stellar bar isn't perfectly symmetrical around SGRA, then the true center of mass of the whole galaxy might be slightly offset from the black hole's position.
Ah, I see. So the S2 measurements give you an ultra-precise distance to SGRA, but if SGRA isn't quite at the galaxy's true gravitational center, that could introduce a systematic difference when you compare these results, or compare them to methods that might be more sensitive to the overall mass distribution.
That's one of the leading ideas, yes. It highlights how reaching this level of precision actually forces us to confront these more subtle astrophysical questions about the galaxy's structure.
Okay, so the super precise measurements reveal a new layer of complexity. This seems like the perfect place for Gaia to step in with a completely different approach.
Exactly. And that's what's so exciting about the recent work by Liu and collaborators, published in 2023, which our sources focus on. They use Gaia data in a completely novel way to get at R0. They don't rely on SGRA or its orbiting stars at all.
No S2, so what do?
Their idea is to use the collective motion, the kinematics, of a huge number of stars within the galaxy's central bar region to directly pinpoint the barycenter of the disk and bar system.
Okay, using the galaxy's own structure to find its middle, essentially. How does that work?
It's pretty clever. They combine data from two massive surveys. First, the APOG survey, which uses infrared spectroscopy to get really good radial velocities, how fast stars are moving towards or away from us.
Got it.
And second, Gaia EDR3, which gives us those incredibly precise, proper motions, how fast stars are moving across the sky, plus parallax information. Now, getting accurate distances for these stars near the center is still tricky, even for Gaia, so they use some sophisticated machine learning, a neural network trained on Gaia parallaxes of closer stars to estimate reliable distances for the more distant stars in the bar.
Okay, so they end up with this massive data set mapping how stars are moving in 3D space in the central part of the galaxy. A six-dimensional map position and velocity for each star.
Exactly, a huge 6D phase-based map of the bar region.
And how do those star movements tell you the distance to the center?
They looked for a specific signature. They focused on the transverse velocity, the speed across our line of sight, for stars that lie along the direction towards the galactic center.
Okay.
Imagine you're driving straight towards a distant mountain peak. As you get closer, its apparent sideways motion against the really distant background seems to slow down, right? It drifts less across your view. Ideally, when you're lined up perfectly with it, its sideways motion is 0 before it starts drifting the other way as you pass it.
Right, I get the analogy.
They applied the same principle to the bar stars. They looked for the distance along our line of sight where the average transverse velocity of the stars moving along that line of sight towards the galactic center reached a minimum. The idea is that this minimum point should correspond to the distance to the actual dynamical barycenter.
Huh. That's a really neat way to use the bulk motion of stars. Very different from tracking one star's orbit. What distance did this Gaia-based method give them?
Their result for R0 is 8.23 plus or minus 0.12 kiloparsecs.
8.239 can 0.12 kpc. Okay, let's put that number into context with everything else we've talked about. How does it stack up?
Well, first off, 8.23 kpc is significantly higher than some of those older, lower estimates we mentioned, like that 7.1 kpc from Olling and Merrifield. This Gaia result seems to pretty definitively rule out those much lower values.
Okay, good. What about compared to those super precise S2 results that are causing all the discussion?
This is the really interesting part. The Liu et al. Gaia result of 8.23 kpc is formally inconsistent with the lower S2 estimate from Du et al., the 7.971 kpc value. Their error bars don't overlap.
Okay, so it disagrees with the Keck S2 result.
Yes. However, it is in remarkably good agreement with the higher S2 estimate from the Gravity-Milky Way collaboration, the 8.275 kpc value. They are statistically consistent within their uncertainties.
Oh, okay. That's significant.
It is. And maybe even more telling, this Gaia-based 8.23 kpc value aligns extremely well with that consensus value, R0 equals 8.2 plus or minus 0.1 kpc, that Bland Hawthorne and Gerhard proposed back in 2016. Remember, that was a consensus value before these latest ultra-precise S2 results from both Gravity and Keck came out.
So let me summarize. A completely new method, using Gaia data and the bulk motion of bar stars, lands on a value that basically agrees with an older consensus figure and one of the two conflicting high-precision S2 results while disagreeing with the other high-precision S2 result.
You've got it.
What does that tell us then? About where the true value might lie or about the methods?
I think it strongly suggests that systematic errors are still the name of the game here, even with these incredibly precise measurements. The fact that a method based on the large-scale structure of the galaxy, the Gaia star method, gives a result consistent with one dynamical measurement, gravity S2, and an earlier consensus. While the two leading dynamical measurements, gravity versus Keck S2, disagree with each other, well, it hints that maybe there are subtle systematic effects or assumptions buried within the S2 orbital modeling that aren't fully captured yet.
Maybe related to that potential offset between SGRA and the true barycenter we talked about, or other astrophysical complexities?
Could be, or maybe differences in how the data is analyzed, how the reference frames are defined. It's complicated, but the Gaia result provides a really crucial independent cross-check that seems to favor the slightly larger R0 values, around 8.2 to 8.3 kLPC.
And the power of Gaia isn't just limited to refining R0 itself, is it? The sources mentioned that getting a better R0 value helps unlock other things Gaia is measuring about the galaxy.
Oh, absolutely. Gaia is delivering so much more than just positions. One of the most mind-blowing results, mentioned in the review, is the direct measurement of the solar system's acceleration as we orbit the galactic center.
Wait, Gaia can measure our own acceleration through space? How on earth does it do that?
It's amazing, right? It does it by looking at the apparent proper motions of extremely distant objects, quasars. Quasars are active galactic nuclei billions of light years away. They are so incredibly distant that they should appear perfectly fixed in the sky. They define a non-rotating reference frame.
Okay, they're like fixed background points.
Exactly. So if Gaia observes a tiny, systematic, collective apparent motion or drift in the positions of all these quasars across the entire sky, that apparent motion isn't because the quasars are moving. It's because we, our solar system, are accelerating as we orbit the Milky Way.
Wow. Our orbit isn't a straight line, it's curved. So we must be accelerating towards the center.
Precisely. It's the centripetal acceleration required to keep us in orbit. Joe Bovee called this measurement a revolutionary moment for galactic astrophysics back in 2020, and Gaia measured this acceleration. It's about 5.05 plus or minus 0.35 microarcseconds per year squared. Tiny, but measurable.
That is just incredible. So how does knowing that acceleration combined with our new R0 value help?
Well, basic physics tells us that centripetal acceleration A is related to orbital velocity v and orbital radius r by the formula A equal v, or the r.
Right.
So if you have a good measurement of the acceleration A from the quasars, and you now have a more reliable value for the radius r, which is our r0, you can directly calculate velocity v.
Ah, so you can calculate the sun's orbital speed around the galaxy.
Exactly. If we plug in the Gaia acceleration, 5.05 ILRE, and use the Loon middle, R0 value of, say, 8.23 km/s, you calculate the sun's circular velocity, V0, to be about 243 plus or minus 8 kilometers per second.
243 kilometers, that's significantly faster than the old standard value of 220 kilometers that was used for decades, right?
It is, yeah. The picture is definitely shifting towards a slightly larger R0 and a faster rotation speed for the sun. You can also calculate the local angular speed, omega 0, which is just V0 divided by R0, and that comes out around 29.3 plus or minus 1.0 kilometers per second per kiloparsec.
Okay, so Gaia helps refine R0, and that, combined with Gaia's acceleration measurement, gives us a better handle on our own speed. What else?
Well, Gaia also measures the proper motion of SGRA itself extremely precisely. Now, if we make that assumption that SGRA is perfectly at rest at the dynamical center of the galaxy...
The assumption that might be slightly off.
Right, the one that might be slightly off. But if we make it for a moment, then any apparent motion we see for SGRA on the sky must actually be due to the sun's own peculiar motion. That is, the sun's velocity relative to a perfect circular orbit at our location. Gaia's measurement of SGRA's proper motion directly translates into one component of the sun's peculiar velocity, VA, giving about 8 plus or minus 8 kilometers in that direction.
So Gaia is providing all these incredibly precise pieces, distances, motions across the sky, speeds towards and away from us, even our own acceleration, and allowing us to connect them all together. The scale of the galaxy, R0, its rotation speed, V0, and our own place in motion within it, V.
That's exactly the point the sources emphasize. Gaia is truly transforming our ability to map out and understand the dynamics of our entire galaxy as a coherent system, refining these fundamental constants in ways that just weren't possible before its data arrived.
It really has been an amazing journey to trace, hasn't it? Following this quest to measure R0, from those very early kind of rough estimates based on where globular clusters seem to be.
Struggling with dust and just the limits of the telescopes back
With the
then.
Hipparcos era, which helped calibrate the tools better than the modern age, with adaptive optics letting us actually watch stars dance around the black hole.
Yeah, the S2 measurements.
And now finally, this completely new angle coming from Gaia, using the motions of vast numbers of stars across the galaxy.
We've seen the precision just skyrocket, especially in the last decade or two, which is fantastic. But as we saw, that incredible precision has actually thrown up new questions and highlighted these subtle but significant disagreements between different cutting-edge methods.
Right. We're left with these really intriguing puzzles like, why do the two most precise measurements using S2 give slightly different answers for R0?
And the deeper question underlying that: is the supermassive black hole, SGRA, truly sitting exactly at the gravitational barycenter of the entire Milky Way? Or is there a slight offset?
These aren't just minor details, are they? They touch on how well we really grasp the fundamental structure and the dynamics of our own galactic home.
Absolutely.
It's just a powerful reminder, isn't it? Even with a mission like Gaia delivering data of a quality we could barely have dreamed of just a couple of decades back, fundamental questions about the true scale and the intricate workings of our own Milky Way are still being actively debated, refined, and explored. The universe, even our closest cosmic neighborhood, still holds mysteries we're working hard to figure out.